How's it going? Good. Everyone seems really excited after lunch. So, like Glenn so nicely introduced me, my name is Gabby Hillyer. I'm a dual degree master's student at the University of Maine. And I have been working with the Medomic project on modeling the circulation of the estuary. So basically, the way this project started out is I was hired by Damian Brady and Bridie McGreevy. Brian Bale is also on my committee, Keith Evans is now, to kind of look at all of the data that was available from the DMR and DEP and the Medomic Task Force and try and fill out the gaps that hadn't really been explained yet. And one of the major questions we still had was, how does this polluted water get out of the estuary, rather than where is the pollution coming from? So we started the idea of building a circulation model for the Medomic estuary. And basically, the goals of this project are to compare closure times for different clam flats with the actual residence time of polluted water in the system. So just to kind of give you guys an idea, that's a map from the DMR of the conditionally closed and restricted flats on the Medomic. Like I said, we started this project by talking with the DMR and DEP, plus Glenn, quite a bit on what was available. And these are the major steps that I'm currently taking and will be taking in the future. So the first thing we did is we interviewed with clammers and met with the Medomic Task Force and the Selectmen's Committee in Waldoboro to try and understand what the major needs were for this community and what they really wanted done, the areas they wanted studied. I then released drifters for a full field season, which I'll kind of explain in a minute what those are and how those work. And then right now we're going to be ground truthing these circulation models that show how the water moves in and out of the system. And then finally we'll be comparing the residence time of polluted waters with the closure times of the clam flats. So the first thing I did was I interviewed 7 key informant clammers to try and get at their observations, if they had seen anything that could have caused the pollution, any strange plants or animals, and I wanted to really understand what the areas they wanted that were reopened. And so just to kind of reiterate, these clammers and these interviews really informed how this circulation model is going to work and where the drifters were deployed. I also worked primarily with Glenn and Abden Simmons quite a bit in the field, retrieving these drifters, and this approach really allowed me to understand the needs of this group and build some very obvious alliances with the community. But so just to kind of give you guys an idea, these are different maps that the clammers themselves drew on, highlighting areas they had seen decline from recruitment, as well as the areas that they wanted reopened. Sorry about that, last one, I don't know why it's so quick. And finally we get to my drifter study. So a drifter is what oceanographers use to kind of see how the water moves. These pieces of technology float in the water at near surface areas so we can see how they move. This bucket drifter is what I use. It was designed by Jim Manning at NOAA and myself. To kind of give you guys an idea, it's a Home Depot bucket that has a brick in the bottom, very scientific. And the top is a buoy, as well as 2 different GPSs. So these GPSs, one is a satellite tracker that I can pull up on my phone and see where these drifters are. And the second is a GPS that gives these nice, smooth data points because it keys in every 30 seconds where exactly it is. So we release these drifters to understand those near surface currents, that freshwater plume, that polluted water, and where it goes. And just to kind of give you guys an idea, this is what they look like in the water. So you can see they aren't truly dragged by wind, but instead by that near surface current. And this is a map of where all of the drifters have been as of September. So in October we did quite a bit of studies inside of here, but you can see they have a pretty wide coverage area. So these drifter tracks will be used to kind of figure out the speed of the water moving. So right now I get to sit in front of a computer rather than be out on a boat. which is not always the best. But so we've kind of come up with a couple of key points from these drifter tracks. First off is that there's a higher speed of water at these constrictions here and here, which seems fairly obvious. We can also see that the mid to upper estuary, basically from here to here, tends to retain water, which is why they're having some pollution issues that Glenn already talked about. And that's also why they have such large clam flats, because the sediment is able to remain in that area. It should be noted that so far, the drifters have been able to leave within 2 to 3 tidal cycles, so 1 to 2 days, when released anywhere along this area. But just to give you an idea of what I'm doing, so this graph over here is speed versus time, and all of those pretty colors, the red, blue, and yellow, are the 3 drifters that were released at the same time. So and the purple line itself is the tidal height. So you can kind of see that the speeds increase as the tide comes in, but they don't increase as the tide goes out, and that's kind of proving that that estuary retains water. To give you an idea of what this map is, it's the same drifter track. We just wanted to highlight where the speed changes geographically. Yes, so the next part is the model, which is a little crazy. But so the first part of any model, for those of you who aren't familiar, is building a mesh. A mesh is a triangular grid that kind of dictates the geography of where that model is going to be run. We use triangles because it can fit a curve really nicely, which is important, as you can imagine, in an estuary. But so this right here is our current mesh. You can see this is the bathymetry data, so basically how deep it is. And it matches up pretty well with field bathymetry and satellite data. There is still some improvements that are working on, but that's kind of our progress as of right now. This is being developed by Wei Lu, who's also in Damian Brady's lab. And this is kind of where we're heading with that model. So on the left here is, again, the Chester River model that Wei Lu is working on, which can show you with arrows how fast and where the water is moving at a variety of different points across the river. This is really important because of a few different reasons. One, it can show how the water is moving if polluted water is coming out or getting trapped in, or if they're flowing out. It could also show answers to different questions like, if you seed at this side, is that water going to flow immediately out and rush away, or is it going to settle out? Things like that. So the next plan is to develop the model to create this kind of velocity picture that we see here. You can already kind of see that these constrictions that create those eddies, which are that circular motion, are being reflected in the medomic. So we think we can get a pretty good picture of what's happening there. So these are kind of the last 3 steps of what I'm working on. The first, Cole Canwick kind of talked about how expensive river gauges can be. The reason that a lot of people are looking at them right now is because they get a better picture of how the river flow changes when there's different storms and tides versus just kind of an assumption that's made on how big the watershed is. So what we want to do is change the drifter speeds to actual flow of water. And the way to do that is this cross-sectional analysis. So basically drawing lines across the medomic to understand the full force of water that's coming at you versus just the speed of that near surface plume. And that is going to lead us to calculate flows under those different environmental scenarios. So like Glenn mentioned, right now the medomic is on a 1-inch 2-week closure system. We can check if that's the most appropriate. We can also see what it would look like under 2 inches, under 3 inches, under 4 weeks, under 2 weeks, under 1 week. We can kind of fiddle around and do quite a bit, which is fun. And then lastly, this will help us calculate residence time of these areas that the clammers wanted to open up and compare that with the closure times. So we can get at that goal of if these are the most appropriate, if they're not, and how to change them. All of the results of this project will be shared with Cole Canwood at the DMR, as well as anyone else who's interested. And yeah, that's where I'm at. Lastly, I would just like to thank my funding sources, the Research Reinvestment Fund and the Diana Davis Spencer Partnership for Sustainable Maine, as well as the Medomic Task Force for all of their help and all of their data. Thank you, and I think I'm ready to take questions.